it's not even like it's not even a fair assessment. It's a let's try this game.
Yeah. So just to let you guys know what this second half of exponents and logarithms is all about, it's basically figuring out how to solve exponential and logarithmic equations to solve real life application questions. So for example, we are going to be dealing with some money questions, some half-life questions with bacteria and different stuff like that. Yeah, lots of different types of examples of how we can apply exponential functions and logarithmic functions. So this lesson is pretty much a review and a bit of an introduction of ways that we can solve the equations. So the first bit we should be familiar with. Let's take a look at 4 to the power of x equals 2 to the power of x plus 3. We have to solve by converting to a common base. So if we have 4 and 2 as a base, what's the common base? 2. Okay, so we're going to convert 4 into 2 squared, all to the power of x, and that will equal 2 to the power of x plus 3. If we have an exponent to an exponent, we multiply them, and we get 2 to the power of 2x equals 2 to the power of x plus 3. Once we have the same base, what do we do with the exponents? Set them equal. Good. We have 2x equals x plus 3. Subtract the x to the left-hand side. 2x minus x is 1x. And we get x equals 3. Okay, part B, we have 27, 9, and 3 as our bases. We need a common base. What are we going to pick? 3. Good. So 3 to the power of 3 gives me 27. 3 to the power of 2 gives me 9. And 3 is just 3. And already has an exponent on it. For power of a power, we multiply the exponents. So for the left-hand side, we're going to have to multiply 3 times 2x, we get 6x. And 3 also by the negative 1, so we get negative 3 as our exponent. And just a review of our exponent laws, when we have the same base 3, and we're multiplying, what do we do with the exponents? Add. Good. Okay, so we have 3 to the power of 2 plus 2x minus 1. We could probably clean that up a bit quicker, and we get 2x plus 1. Okay, now we have the same base, so we can set the exponents equal. 6x minus 3 equals 2x plus 1. So I'm going to move the 2x to the left-hand side by subtracting, and I get 4x minus 3 equals 1. Then I'm going to add the 3 over, and I get 4x equals 1 plus 3 is 4. Divide by 4, x equals 1. How's that review? Does it seem fairly familiar? Okay, then we encountered some situations where we can't actually solve using a common base. For example, if we had 2 to the power of x equals 50, can you guys think of any exponent 2 to the power of something that gives you 50? Okay, so let's just think about this. Okay, that will not equal 50, basically. Okay, there's no exponent that's going to set that equal to 50 as a whole number, but there will be a decimal. So let's just see if we can figure out approximately what decimal that's going to be. So if we go 2 to the power of 4, we get 16, so that's a little bit off. 2 to the power of 5 equals 32. 2 to the power of 6 equals 64. So our exponent will be somewhere between 5 and 6. So let's just play around a little bit. Okay, let's go 2 to the power of 5.5. See what we get. What do you get? 45? Okay, how about 2 to the power of 5.6? Exactly?
Well, no, it's like 48.5.
48.5. Gonna say. Okay, what about, we're getting closer. If you did 2 to the power of 5.7, do we go over 50? Yeah, so maybe we'll try 2.5, or 2 to the power of 5.65. 50 exactly? 50.21. Okay, and they're saying to the nearest tenth. So I guess if we're looking at the closest exponent, 5.6 would be our closest. We're going to now figure out what's the exact using logarithms. Okay, does that seem a bit painful having to guess and check what that exponent would be? A little bit. And you won't have time on your diploma to be guessing and checking like that. Okay, so we learned how to solve questions like this using logarithms. And before I introduce something new, I'm going to review what we've learned already. So we have 2 to the power of x equals 50. I need to put that into a logarithm. So I have logarithm base 2 argument 50 equals x. So I'm going from exponential form to logarithmic form because in exponential form I couldn't have solved for that x. But in logarithmic form I have x equals now. Then I'm going to use change of base identity. So I have log base 10 50 divided by log base 10 2. And I can just throw that into my calculator. Okay, so it's always log of the argument divided by log of the base. And I've changed the base to base 10. So if you calculate log 50 divided by log 2, what do we get?
5.6438.
5.6438, probably keeps going. And the answer needs to go to the nearest tenth, so we'll say 5.6. Just so you guys know, if they ever ask you for an exact solution and it's logarithms, this would be your exact right here. Exact form, you can't have decimals. So you would have to leave them as a logarithm. So this is what we've learned already. Now I'm going to introduce something new. It ends up being the same thing, okay? But it's a strategy that will help with some solving later on. So we're starting with 2 to the power of x equals 50. What we can do is we can apply a logarithm to both sides of the equation. Okay? Anything you do to one side of the equation, you have to do to the other. So instead of 2 to the power of x equals 50, we now have a logarithm base 10, argument 2 to the power of x, equals logarithm base 10, argument 50. Okay, so we've just applied logarithm base 10 on both sides. Similarly, like say I had x equals 7. If I add a 3 to this side, I have to add a 3 to this side as well, so that the value of x stays the same. So similarly here, if I'm creating a logarithm on one side, I have to create a logarithm on the other side to balance it. Okay, going from this step to this step, does anyone recognize any of the laws that's been applied? In the power law, taking the exponent x and just moving it out front. How can I isolate x now? I have x multiplied by log 2, so I can just, divide. So x equals log 50 divided by log 2. So that would be the exact answer. And if you calculate it, log 50 divided by log 2, you get the 5.6, which we solved for already. So very similar ways, they end up with the same outcome, but just a little bit different because we're applying a log on both sides. because it's new, why don't we practice that technique for this next question? We have 4 to the power of x equals 12. We need to figure out the exact value of x and the value of x to 3 decimal places. So what we're going to do is we're going to apply a logarithm on both sides. We got log base 10, argument 4 to the power of x, equals log 12. We're going to apply log base 10 on both sides. And step 1. Step 2, we're going to use the power law. And step 3, we're going to solve for x. Okay, so step 2, power law. We're going to take this exponent x and we're going to move it out front. We get x times logarithm, argument 4, equals log, argument 12. Lastly, in order to solve for x, we've got to divide by this log 4, cancel it out on the left-hand side, and whatever we do to one side, we must do to the other. So x as exact form equals log 12 over log 4. And 3 decimal places, can you help me out? Calculate that for me to 3 decimal places. Sorry? And to 3 decimal places? Good. Okay, for part B, we have 8 to the power of x plus 4 equals 40. What you first want to do is isolate the exponent. So this plus 4, we can move to the other side, and then we just have 8x on the left-hand side. So let's rewrite as 8x equals 40 minus 4 is 36. So just subtract 4 on both sides. Do you guys want to try the other way or practice this one more time? Practice? Okay, so again we're going to write it as a logarithm on both sides. We have log h to the power of x equals log 36. Joe's, what do I do next? Power law, good. So x goes in front, multiplied by log 8. Okay, took that exponent, moved it out front. And that equals log 36. Then to isolate the x, I just divide by log 8. So x equals log 36 divided by log 8. That's exact form. And when you calculate log 36 divided by log 8 to 3 decimal places, what do we get? 1.723. We all agree? Yeah. Okay, so we're just going to keep applying that scale. We're going to go log base 10 on both sides. So log base 10, 6 to the power of 3x equals log base 10, argument 3 to the power of 2x minus 1. So I'll rewrite all the steps for this one too. Okay, so we're going to apply log base 10 on both sides. Step 2, we're going to use the power law. So the exponents will be multiplied as coefficients out front. Now I have 3x multiplied by log 6 equals 2x minus 1 times log 3. The whole goal is to solve for x, so somehow we need to isolate the x. Right now we have x in a binomial, And we have x as a, I guess a monomial that's multiplied by the log. So somehow we have to get the x's together. To do that, we're first going to distribute the binomial. So the left-hand side will stay the same. We still have 3x times log 6. What we're going to do is just multiply 2x times log 3 and negative 1 times log 3. So when we do that, we get 2x log 3 minus log 3. How are we doing so far? Yeah? Okay, then we want to combine common terms. So we're going to put all the x's together. So move terms with x to one side. And once we do that, we're going to factor out x. So let's subtract 2x log 3 to the left-hand side. And I have 3x log 6 minus 2x log 3 equals negative log 3. Now I have two terms that have x in it, so I can just factor x out. I'm left with 3 log 6 from my first term when I factor x out. And negative 2 log 3 from the second term when I factor x out. Remember, factoring is like dividing. And that's equal to the right-hand side, which is negative log 3. It's a long one. We're not done yet. Okay, we still have to get it in the form log m divided by log n as exact form. So we're kind of working in reverse now. We did the power law one way, now we've got to reverse it. So again, we're going to use the power law. Okay, so x is going to be on the outside. And I have log 6 to the power of 3 minus log 3 to the power of 2. That's going to equal this negative. It's going to become an exponent. So we equal log 3 to the power of negative 1. So we took all these coefficients and we moved them as exponents. Okay, so we applied the power law. Chris, any questions? Okay. So next step, 7. What do we have here? Logarithms with the same base. And whenever we're subtracting logarithms with the same base, what law can I use?
Quotient.
Quotient law. Good. So I have x multiplied by log 6 to the power of 3 over 3 to the power of 2. And that equals log to the power of 3 to the power of negative 1. It's really like 1 over 3, right? Let's just clean things up a little bit. Okay, if you go 6 to the power of 3 divided by 3 to the power of 2, or 6 to the power of 3 divided by 9, what do we get?
24.
24. Okay, good. Now we're getting a little bit cleaner, and we can just divide by the log 24 to get x all by itself. So last step, isolate x, or solve for x. So x equals log 1 over 3 divided by log 24. And if we calculate that, okay, this is our exact answer. If we calculate nearest 3 decimal places, we get negative 0.346. And if you didn't get that, just be careful with your brackets. Make sure it's this log and I guess just make sure that you close the 1/3 before you divide the second logarithm. You don't need a bracket around all of it. So how are we feeling? Might seem a little intimidating at first. Keep in mind you do have the power laws on your formula sheet, the power law, the quotient law, the product law. However, if you know them off by heart, you're going to be able to do this a lot quicker and you're going to be able to think creatively on how to solve these. If you don't have those laws ingrained in your head, then you might be stuck for quite a while. So please make sure if you haven't done lesson 7 and 8, which I believe is on laws of logs, you need to practice them in order to do well on solving equations. So we're going to do one more. Steps are going to be very similar. And I'm going to see if you guys can help me out as we go through. So hopefully you guys have a bit of space. If not, in the back of your workbook, I think there's some note pages. You can just leave yourself a note that the solution to this one are on your note pages. So what have I done to every single equation to solve for x when it's in the exponent and there isn't a common base? What have I applied to both sides? Log. Good. Okay, so I have log 2 times 3 to the power of x minus 2 equals log 7x. Now, before I apply the power law, I want you guys to recognize that this here is actually argument 2 times 3 to the power of x minus 2. So before I apply this exponent in the power law, what I can do is break it up into the product law. Okay, so once I apply the product law, I'm going to get log 2 plus log 3 to the power of x minus 2. And that equals log to the argument 7 to the power of x. So first I'm applying log to both sides, then I'm going to split up this these factors in the argument into the product law. Now I can apply the power law. Okay, so log 2 will just stay log 2. I'm going to take this exponent, put it up front, x minus 2 times log 3. And that will equal x. I'm moving the exponent as a coefficient out front, so x times log 7. The whole goal is to solve for x. In this case, I have a bit of a problem because I have a binomial. What did we do in the last question? Distribute. Good. Okay, so let's just expand here. We end up with log 2 plus x log 3 minus 2 log 3 equals x log 7. Again, the goal is to solve for x, so anything that has an x, any terms that have x with it, we have to move to the same side. So let's subtract x log 3. I'll cancel it on this side, and I'll subtract it on this side. And I have log 2 minus 2 log 3 equals x log 7 minus x log 3. Okay, let's just talk about the right hand side to start off with. I'm running out of room on the camera, so I'll just shift it. Okay, so on the right hand side, we want to factor out the x from these two terms. Okay, so if you factor x out of the first term, we're left with log 7. And if we factor out an x from the second term, we're left with negative log 3. On the left-hand side, we have log 2 minus, do you guys mind if I just put the power law right now? So taking this coefficient, moving it to the exponent. So we get minus log 3 to the power of 2. So in this step, we factored out x. And we did the power law. We're subtracting logs at the same base. What can I do with them? Quotient law. Good. So on the left-hand side, we have log 2 divided by 9. Okay, because 3 squared is 9. And that will equal x times log 7 over 3. The final step is just to isolate x. And if we do that, we get log 2 over 9 divided by log 7 over 3. That's our exact form, and we just need to calculate to the nearest 3 decimals now. What'd you get? Did you calculate it? Okay, negative.
1.7 or 1.8 or sorry, 7.8.
So 3 decimals, we have negative 1.775. And just remember, anytime you're taking a logarithm where it's between 0 and 1, you end up with a negative log.
Junior class change.
So we've pretty much done example number 2 already, so skipping forward to example number 3. Gets a little bit easier, don't worry.
Oh, I don't know, right? Oh, I just typed it in.
Alright, we're getting into a formula that's going to be useful when we look at some financial questions in the next lesson. But here they're giving us the formula, so we don't have to think too hard. Okay, according to Statistics Canada, in the 21st century, Canada's population has been growing at an average annual rate of 1%. The exponential equation, p equals p0 multiplied by 1.01 all to the power of n, can be used to predict the population, p, n years after known population, p0. So p0 is pretty much like the starting population. P is what it's going to get to, and n is the number of years. Okay, some of you really hate word problems. Pretty much you can cancel all of this out. These are important because they're telling us what the letters mean, but this equation is the most important. Okay, now they're giving us the information. They're telling us that the population at the beginning of 2001 was approximately 30 million. We're going to estimate which year the Canadian population will reach 50 million, assuming the same average annual growth rate each year. Okay, so let's just start with our formula. We have P equals P at the beginning of their time that they're calculating, multiplied by 1.01 to the power of n. they're telling us that in 2001, which will be our P0, that's equal to 30 million. They're telling us that what we want to grow to is 50 million. And they're asking which year we will get to 50 million.
Excuse the interruption. Could the Bantam varsity students please come down to the main office? Thank you.
Oh, it's loud. Alright, so they're wondering which year. So eventually we're going to have to figure out which year it actually is, but n is the number of years, so we'll solve for that first. So let's just plug in what we know. Okay, we know our P is equal to 50 million. Okay, P at 0 time is equal to 30 million. That's multiplied by 1.01 to the power of n. Okay. Just like we did in some previous questions, we first need to isolate the exponent. So we want to get 1.01 to the power of n all by itself. So we're going to divide by 30 million, big number, on both sides. I'll cancel out on the right hand side. Now we're left with 1.01 to the power of n equals 5 over 3. Taylor, where are you going to be?
I just need the homework.
Yeah, which class are you in right now?
But I'm going there to grab all of the homework.
Okay, can I find you at the bell?
Yeah.
Okay, thanks. Okay, now we have 5/3 equals 1.01 to the power of n. So, do you think there's any common base that we could use? No, so we have to use logarithms. You can apply a logarithm to both sides, and maybe because that's what we've been doing in class, let's do that. Okay, so we have log 5/3 is equal to log 1.01 to the power of n. Then we're going to use the power law.
What did you get?
Put n out front. And then we just have to divide by log 1.01. So log 5/3 divided by log 1.01. And what do we get? What? Okay, sounds good. Okay, so we got 51 basically. There's a bit of decimals, but they're asking in what year. So it's not good enough just to solve for n and say 51.337 something 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 years. We have to figure out what's the actual year. So we started out in 2001. Okay, then we're adding 51.337 years. So we end up with 2052, our final answer. Okay, now is it going to occur, is this population of 50 million going to happen right at the beginning of 2052? No, because we have to account that these decimals here represent months. Okay, so it's going to be sometime in 2052. Next lesson we'll get into the months. How are we feeling so far? We're skipping the next example because that's dealing with the natural logarithm, e. And I'm just going to show you guys how, when all else fails, you're back up. How to solve for these using your calculator. Okay, and it's really good to understand how logarithms and exponential functions look. So although it's kind of a cheat to use your calculator, you still have to understand what's going on. Okay, so say for example we had to solve 4 to the power of x equals 7. we need to figure out what value of x will satisfy so that left-hand side equals right-hand side. There's two ways we can solve. There's the intersection method and the zero or the x-intercept method. Let's start with the intersection method. Basically, you need to take both sides of the equation and set them to be a graph. So y1 will be equal to the left-hand side, so 4 to the power of x, and y2 will equal 7. And when you graph those, we should know that the exponential function will go through y-intercept of 1. It will be greater than the x-axis and look something like that. Okay, and then y2 is just 7, so when y equals 7, the graph will look like this. The whole goal is to figure out what is the intersection point. So to do that, you're going to go second trace, and number 5 for intersect. We already know that y is going to equal 7. We just need to figure out what's the x value. That's the whole goal of this, solve for x. So what do you guys get to the nearest tenth? 1.4? Okay, so x equals 1.4, while y equals 7. We just care about the x. The next technique is the zero method, and we just need one graph. So if 4x equals 7, we're going to move everything to the left-hand side. So we got 4x minus 7 equals 0. And the graph that you're going to put into your y1 is 4x minus 7. So we're taking this exponential function and we're just dropping it down 7 spaces, like we learned from our transformation unit. Okay, so if our intercept was at 1, it's now at -6. Thank you. And the zero method, that's another term for saying find the x-intercept. So on your calculator, to find the x-intercept as a review, we go second, take, trace, number 2 for your 0. Then it's going to ask for left bound, right bound, and then a guess. So left bound of this x-intercept will be below the x-axis, right bound will be above, and then guess will be somewhere in between. And when you go through those 3 steps, you should get x is equal to 1.4 and y equals 0. We're only concerned with the x value. That's what we're trying to solve for. Okay, we could solve this algebraically, but we've done a ton of that today. So I think you guys would be able to do that as well.